How to solve circuits the right way, once and for all. Lecture 3. This is Vachevorperian with the joys of circuits analysis. The material in these lectures is covered in my book, Fast Analytical Techniques in Electrical and Electronic Circuits, published by Cambridge University Press and available from any bookseller. In this lecture, I'm going to introduce and prove the Extra Element Theorem. This lecture comprises 2 videos, and in the first video, I'll first introduce the concept of nulling a response by 2 excitations, and the concept of a null impedance looking into a port of a network. Second, I'll talk about nulling the voltage or current of an impedance element. Third, nulling the voltage across an independent current source, or the current through an independent voltage source. Fourth, I'll talk about modeling an impedance element with dependent current or voltage sources. In the second video, I'll introduce the general proof of the EET, and then I'll work out an application of the EET to impedance elements in the determination of a transfer function, and then application of the EET to dependent sources in the determination of a transfer function. We begin with nulling a response by 2 excitations. This is what Dr. Middlebrook called Null Double Injection. Here we start with the block diagram of a linear time invariant circuit to which we're going to apply 2 excitations. The first one, which we call input 1, is an arbitrary excitation which could be either a voltage or a current source. The second one that we're going to apply is specifically a current source excitation applied to port 1 of this linear time invariant circuit. In addition, we will consider 2 responses inside the circuit. The first one is an arbitrary response, which we call output 1, and that could be the voltage at a node or across an element or the current through a branch. The second one will be specifically the voltage that arises across the applied current source at port 1. Hence, we have 2 responses. V, the voltage that appears across the independent current source applied to port 1, and the second one, some arbitrary response inside the circuit, a voltage or a current. Now, because of linearity, we can write each one of these responses as a linear combination of the 2 excitations being applied to the circuit. Output 1 is the linear combination of the contribution of input 1 plus the contribution of the current source applied at port 1. The second response, which is the voltage that appears across I, itself also is a linear combination of the contribution of input 1 to that voltage there and the contribution of I to that voltage there. We will now interpret each of these coefficients as some kind of a specific transfer function of this linear time invariant circuit under a specific condition. For example, A11, shown here, is the transfer function from output 1 to input 1 when the second excitation is set equal to 0, when I equals to 0. You can see that from this equation here. On the circuit diagram, you see that this is indeed a transfer function on this linear time invariant circuit with port 1 open circuited. The second one is A21, which is the voltage that appears as a response across port 1 because of excitation input 1 applied, while the second excitation I, the current source applied to this port, is set equal to 0. So this is a second transfer function that we see on this linear time invariant circuit from input 1 to voltage V, the second response that we considered. If we go to the third coefficient, we see that this is the transfer function from the first output to the second excitation I being applied to the circuit, while the first excitation is set equal to 0, or the first input set equal to 0. Of course, that means that if this was a voltage source, that port there would be short-circuited, and if this was a current source, that port would have been an open circuit. Nevertheless, this is another transfer function defined on this circuit. Finally, the last one, A22, we see that it is the transfer function from the second response to the second excitation being applied to the circuit, while the first excitation is set equal to 0. And this is the familiar driving point impedance looking into port 1 of the network. So we would like to interpret or think of these coefficients as different transfer functions that can be defined on this circuit under certain specific conditions of port 1. We now adjust these two excitations, input 1 and I, being applied to LTI in such a way to reduce output 1 to 0, or a null. What this means is that what you are doing is canceling the contribution of the first input to the output by the contribution of I to the output. This should be possible, as you can see from these two linear equations that you write down. When you set output 1 equal to 0, you find a relationship between these two excitations, input 1 and I, which tells you that input 1, when it is equal to the negative of A12 divided by A11 times I, that is the relationship between these two excitations, the output will be nulled or reduced to 0. Now, I want to tell you this from the very beginning. All you have to know is that this is possible to do. You will never ever have to use this relation anywhere in your application of the extra element theorem once you know it. All you have to know that it is possible with two excitations to set any response to 0. And you move on from there. You don't get into the nitty-gritty of how did this happen. You just know that it happens, you assume it happened, and you move on from there. You will see this in the application of the extra element theorem. Now, with this condition satisfied, meaning with the two excitations being adjusted in a way to set a particular response to 0, I can now define under these conditions the ratio of the second response to the second excitation, which is the ratio of V to I. And this is the definition of the null driving point impedance looking into port 1. This is defined then as, and we designate it with the script Z, super 1. The super represents the port where this is being performed, this null impedance calculation. It is the ratio of V to I when the response output 1 has been set equal to 0. You can solve that from these two equations and find out that it is indeed equal to A22 times A11 minus A21 times A12 divided by A11. Now, I'll tell you from now that the calculation of the null input impedance is not performed by doing this algebra. This algebra will yield Z1 correctly, but that's not the way it's going to be done. What this is telling you is really the other way around. The algebra of A22 times A11 minus A21 times A12 divided A11 is the null impedance looking into port 1, which you can perform on the circuit diagram. Very important for you to realize at this point. This is an operational method. Null impedance looking into a port of a network is an operational method, meaning you go on the circuit and you do some circuit analysis to actually figure out this complicated mathematical expression. So the null impedance looking into port 1 is an operational way of performing this algebra on the circuit diagram rather than actually sitting and cranking out pages of algebra doing A22 times A11 minus A21, A12 divided by A11, as you can suspect, this is some kind of a determinant, and it can be a huge determinant depending on the complexity of the circuit. And it's something that you're not going to have to do. It is something that's going to be like doing the algebra on the circuit diagram. And that is the importance of the null impedance looking into a port of a network under conditions of a particular response of that network being nulled. Let us now compare the two impedances looking into port 1. The ordinary driving point impedance looking into port 1 and the null driving point impedance looking into port 1. Here is the ordinary impedance looking into port 1 of a network. You go at that port, you set any independent excitation in the rest of the network equal to 0, you apply a current source, and you study the response V across that current source I. The ratio of the two is the ordinary driving impedance looking into port 1. And it's unique. There's only one ordinary driving point impedance or normal driving point impedance looking into port 1. When you compare this to the null driving point impedance looking into port 1, you realize that this depends on which response in the network you set equal to 0. This excitation, input 1, when being applied to this network, generates all kinds of responses inside that network. You can pick different responses anywhere inside this network and null that one with I and V being applied at the same time. And in each case, you will get a different null driving impedance looking into that port. So the ordinary driving impedance looking into port 1 is unique, whereas the null driving point impedance looking into port 1 of this network is dependent on which response in that network you set equal to 0. And the best way to understand this is by way of examples, as we're going to show next. We are now going to demonstrate these two driving point impedances, the normal and the null, on this circuit that we've seen before, in which there's an excitation V being applied, and there's a port in this circuit that we're considering, which we call port 1, and a response V0. So the first excitation is V in, and the first response we're going to consider is the voltage across V0. At port 1, we're going to say, what is the ordinary impedance looking into port 1? And what is the null driving impedance looking into port 1 with V0 nulled? Well, let's do that. The normal impedance looking into driving point impedance looking into port 1 is obtained by setting the excitation here equal to 0. You connect the test current source here and study the voltage across it. I don't have to do that for this simple network because you can do this by inspection. Because you see, when you set the input equal to 0, you take R3 and put it in parallel with RL. Walking back, you have R4, and at this node here, because we've shorted this one down to ground or return, then R1 is connected between this node and ground here. So it is quite clear that R1, the ordinary impedance looking into this port 1, is R2 plus R1 in parallel with R4 plus R3 parallel RL. It's something you can write by inspection. So I did not have to actually connect a test current source here and solve for the voltage across it and divide the two. Sometimes you have to do that, of course, if the circuit is a little bit more complex and you cannot straightforward see series parallel combinations. So this is the driving point impedance looking into port 1 of this network, in which V in is the excitation being applied at this port. And it doesn't care where you are picking up for a response inside this circuit. And now we're going to perform the null impedance calculation looking into port 1. To do that, I will connect a test source here and determine the ratio of the voltage to that current appearing at that port. In my previous slides, I was always showing this as a test current source and studying the voltage across it. Purposely, I did this so that you can understand that whenever you're performing an impedance calculations looking into a port of a network, you have the full freedom to choose a voltage or a current source connected at that point. Or you may just connect nothing and do it by inspection. So it is immaterial what you connect at that port to do an impedance calculation. You have the full freedom to do whatever you like. That's why I put here a voltage source instead of a current source, and I'm going to study the ratio of Vt to It. Now that I have two excitations being applied to this circuit here, I can null the response V0 and determine the ratio of Vt to It. Now I can simplify my work a little bit, and that is by recognizing R2 appears as the first resistance that I'm going to be seeing, no matter what turns out for this expression R1. So I don't have to carry R2 in the algebra that I'm going to perform on the circuit diagram. And I'd say, why don't I take R2 out of the picture and perform R prime super 1 instead of R super 1 here, without R2 being carried out in the algebra that I'm about to perform. When I do that, I take R2 out and I perform the calculation for R prime super 1, looking into port 1 with the response V0 nulled. V0 has been nulled. So now that it has been nulled, what follows? It follows that the current through it goes through 0. When the current through this branch goes through 0, and the voltage at the same time is collapsed to 0, then the applied voltage V prime t at this point appears directly across R4, and obviously it will start a current through it given by V prime t divided by R4, Ohm's law. And that current, interestingly enough, when it reaches this node here, will turn around and flow through R3 entirely because there is no current flowing through RL. And in doing so, it will create a voltage drop across R3 given by V prime t divided by R4 times R3. When that happens, the voltage that appears across R1 as a result is the sum of the voltages across R4 and R3. And the sum of those two voltages is V prime t plus V prime t divided by R4 times R3. So when I add these two voltages together and divide by R1, I will get the current I prime t flowing through R1. Pretty straightforward. And that gives me the relationship at this node I prime t between these two currents and I prime t. So this current here on the right was V prime t over R4, and this current here is the current through R1, which is the voltage that appears across R1 divided by R1. And the voltage that appears across R1, as we said, is the sum of these two voltages, the one across R4 and the one across R3. You add these two, here they are, you factor out V prime t, divide by R1, and you get I prime t. And sure enough, the ratio of the two is the null driving point impedance looking into port 1. It is given by 1 over R4, the 1 over R prime 1 is given by 1 over R4 plus this expression here, which tells me that it is the parallel combination of R4 and R1 divided by 1 plus R3 over R4. So this is doing the algebra on the circuit diagram, and it results in this expression for R prime 1, and therefore R1 is given by this. And this is the null driving point impedance looking into port 1 of this circuit here with V0 nulled, where V0 is the voltage across RL. And now we're going to null a different response inside this circuit here, which is going to be the voltage across R3, to show you that the expression that you get for the null impedance looking into port 1 is different than the one before. And as usual, when we perform this calculation, we can take R2 out of the picture because it appears directly in series with this calculation here. So we perform the algebra on a simpler circuit with R2 taken out. And in this circuit, we're going to null the response V0, which when we do, results in a zero current through R3. When you do that, this wire here is kind of dangling out there doing nothing, and the voltage V prime T, which appears across R4 and RL, will generate a current through it, which is V prime T divided by R4 plus RL by Ohm's law, and you have a voltage division between R4 and RL of the voltage V prime T, which we write on the circuit shown here across R4. This voltage will get impressed on R1 because V0 is 0. So going around this loop here, this voltage appears directly across R1 and it will start a current through it. So I know the two currents out of node A going to the right and to the left. And the sum of those two is equal to the current coming out of this generator V prime T, so that I can write I prime T is this current, which is this current here. I divide and multiply by R4 because I'm going to factor this expression in the next line here. And this current here, which is going to be the voltage across R1 divided by R1. And when I factor R4, I get this expression for R prime 1 looking into this port here. And I add to it R2, and I get this different expression for the null impedance looking into port 1 of this network. We will now demonstrate the concept of a null driving point impedance and an ordinary driving point impedance looking port 1 of this ideal op-amp circuit. First, we'll consider the ordinary driving point impedance, as shown here, whereby I connect the test current source IT connected across port 1, and I'll study the voltage VT across it. Since this is an ideal op-amp, the differential voltage appearing at its input terminals is 0. And therefore, the voltage across R1 is 0, and consequently, the current through it is equal to 0. So at this node here, going to the left, there's 0 current going out that way. Likewise, there's 0 current going into the op-amp, even if that op-amp had finite impedance between inverting and non-inverting terminals internally. That current still would have been 0 because the differential voltage appearing across its input is 0 by virtue of its infinite gain. So the total current out of this node here is 0. That makes the total current coming out of resistor R2 into this node here 0. That brings this node here down to ground potential. No voltage across R2, no voltage across R1, and this point goes down to 0, and that sets VT equal to 0. And that will make the ordinary driving point impedance looking into port 1 equal to 0. If you're wondering what happens to the current IT, well, it goes all through the output of the op-amp, and the output voltage of the op-amp will be minus ITR3, but nobody cares about that. It's good if you know it so that you won't be confused, but you don't care about that as far as calculating the ordinary driving point impedance looking into port 1. And now I'm going to calculate the null impedance looking into port 1 of this circuit. And to do so, I'm connecting a test voltage source VT across port 1. And I'm doing this on purpose, alternating between voltage source and current source in the determination of an impedance looking into port, to let you know that you have the full freedom to do either way. Connect the test voltage source, connect the test current source, perhaps just use inspection and looking at it. Doesn't make any difference how you go about calculating this impedance here. So when I connect the test voltage source VT here and with V in together, I can null the response V0. And again, it doesn't matter how these two are adjusted. All you know that is that it is possible to null V0. And what happens afterwards is what counts. Now then, when V0 here goes to 0, you immediately see that this voltage VT will appear across R3, and it will start a current through it, VT over R3 by Ohm's law. Likewise, because this is an ideal op-amp and the differential voltage at its input is 0, Vt also appears across R2, and it will start a current through it, Vt over R2. The sum of these two currents is It, and therefore the null impedance looking into port 1 is an easy calculation, and it turns out to be nothing more than R2 parallel R3, which is quite different than the ordinary impedance looking into that point, which was 0. Up until now, we have been nulling the voltage across an impedance element, or equivalently the current through it. We can also, however, null the voltage across an independent current source, or the current through an independent voltage source. And as we shall see, this is a degenerate case. Here are the key points. So far, we learned about nulling the current or voltage of an impedance element, which Dr. Middlebrook called the process Null Double Injection. With two excitations in the circuit, one can choose to null the current through one of these independent excitations if it's a voltage source, or the voltage across one of these excitations if that is a current source. Now, these cases are degenerate in the sense that they are trivial. When we null the voltage across an independent current source, you simply replace that current source with a short circuit. And when you null the current through an independent voltage source, you simply replace it with an open circuit. Your null calculations turn out to be single injection calculations with the other excitation being removed from the circuit as a short or as an open, as just discussed. When we null the voltage across an independent current source, which we show here below, here's my linear time invariant circuit. Here are the two excitations, input 1, input 2. Input 1 is a current source. And here are the two responses, output 2 and VO1, output 1. That's a response of the circuit to these two excitations, just like this is a response here. And I can adjust this current source here with respect to input 2 to reduce the voltage across it to 0. When you do that, this is equivalent to replacing this entire current source with a short circuit and just performing all your calculations in this circuit here just with UI2 present. And this is why we call this a degenerate case, meaning that the null calculations do not involve the presence of the second excitation. The proof of this is pretty straightforward. It is the substitution theorem, and you work it backwards. If I have a circuit this way, where there's a branch, obviously the voltage across that branch is 0, and I have this excitation input 2, called input 2, being applied to this circuit, there's going to be some current flow here in this branch with 0 voltage appearing between these two nodes. The substitution theorem tells you you can replace any such branch in the circuit with a current which has 0 voltage across it, and its value is identical to the current that you get for what you get with the presence of this input 2 inside the circuit here. So whatever current you calculate in this branch, you can take this branch and replace it with a current source equal to the current that you get here, and nothing changes. That's the substitution theorem. It's straightforward. You can try this. If you don't believe it, it may sound strange to you. Well, simple circuits. 2 resistors, 3 resistors, and you can see that this is true. You can do it with a voltage divider. Very straightforward. You should try it. The dual picture applies to an independent voltage source. now I have my first input, instead of being a current source, is a voltage source. And my first response is going to be the current through this voltage source. The second response is anything inside the circuit. So two excitations, an arbitrary input 2 and a specific input 1, which is a voltage source here. Two responses again. One of them an arbitrary response anywhere inside the circuit, a voltage or a current. And the first response, the first output, is specifically the current coming out of this voltage source here. And now I'm going to say with these two excitations, input 1 and input 2, I can null this current here. I can reduce it to 0. When you do that, this is equivalent to opening this branch here. So whatever equations you write for this circuit and whatever equations you write for this circuit are identical. Again, this is by the substitution theorem. And you can try this, as I say, with the simplest possible circuit that you can think of. Do it with a voltage divider. Do a voltage divider between two resistors, R1 and R2, across a voltage source V. Find the voltages across R1 and R2. Then take R2 out and replace it with a voltage source equal in value to what you get from that voltage division. You find out that the current that you will compute through the first resistor R1 will be the same as if you had two resistors in there or two voltage sources, the first one V1 and the second one, replacing R2 with a value equal to what you get from the first voltage division, input voltage V times R2 over R1 plus R2. You put that voltage source there, you get the same current flowing in the branch. And that's the substitution theorem. You can go back to your old circuits book and review that. That's one of the simpler theorems to review, and is a good place here to apply. So now, for this circuit that we saw before, and we nulled the output voltage across RL, and when the voltage was across R3, we nulled that one, and we calculated the null impedance looking into port 1 with those two different responses being nulled. Now we're going to target the current flowing out of V in into the circuit as the second response. And we want to null that one, looking into port 1. So the ordinary impedance looking into port 1 is the same as before. That's nothing changes there because the excitation is V in. You look into port 1, you set that guy equal to 0, and you get that one as before. So that's just a review. Now the null impedance looking into port 1, with this current here being nulled in the presence of this voltage source here, when you null that, the calculation is equivalent to opening that port there. And when you do that, the null impedance looking into port 1 now is a straightforward calculation, which is R2 plus the parallel combination of R4 with R1 plus R3 in series with RL. Now I'm going to review the concept of modeling an impedance element with dependent sources. You can model an impedance element either with a dependent voltage source or a dependent current source. This concept is crucial to the understanding of the proof of the extra element theorem and its application. So if I start with an impedance element Z by Ohm's law, I know that the voltage V is I times Z, or if this is R, I times R. And I can model that with a dependent current source I that talks to the voltage across itself V. I equals to 1 over Z times V, so this is a dependent current source with a gain 1 over Z. Very basic. I can model this with a block diagram for what it's worth. Here I have a linear time invariant circuit with some input UI1 and some response output 1. I can make this excitation being applied to the circuit dependent on some response inside the circuit, which I call output 1. So I can convert on a block diagram an independent excitation being applied to the linear time invariant system by making it equal to some gain multiplied by some response inside the circuit. You convert it to a dependent source, from an independent source to a dependent source. And when you specialize this picture here to this one here, to this dependent current source that talks to the voltage across itself, you get that gain alpha equal to 1 over Z. The dual picture of what we just said using a voltage source is shown here. I can take an impedance element Z and by Ohm's law say that it can be modeled with a dependent voltage source V, which talks to the current through itself with a gain Z. Straightforward Ohm's law. There's nothing else to it. And we can show this on a block diagram like before. I have some linear time invariant circuit to which I'm applying some independent excitation input 1 and some response output 1. And then I decide to make this independent excitation depend on this response 1 through a gain alpha. And that way I have converted this independent excitation to a dependent excitation with a gain alpha. And when you specialize this block diagram to this picture here, you see that alpha is equal to Z, or 1 over Y, the conductance of this impedance element. A very nice simple application of what we just said is for the diode-connected bipolar junction transistor, which is the way you make diodes inside integrated circuits. You short the collector to the base. For the diode, for the transistor rather, BJT, its equivalent circuit model is given by this picture here. You have a transconductance with gain GM, which produces a current in the collector by talking to the voltage across base emitter, which we call V pi. Now, when I short the base to the collector, I'm impressing this voltage V pi across the current source itself. So now, this current source, GM, is talking to the voltage across itself. V pi becomes the voltage across itself. And when you do that, that current source can be replaced by a resistance 1 over GM. And the equivalent resistance between the collector and emitter with the base collector to the short is the parallel combination of R pi with 1 over GM, which is the dynamic resistance of the diode, base emitter diode, with the current in the diode being the emitter current. And now we're ready to move on with the proof of the extra element theorem and its application to transfer functions, as I will show you in the next video.